students, in this video we are going to derive degrees of freedom for a certain system. Phase rule is F is equal to C minus P plus 2. C is number of components present in the system, P is the number of phases, and 2 represents temperature and then pressure. In certain cases where there is no vapor phase existing, we need to use condensed phase rule, which is F is equal to C minus P plus 1. 1 represents only the temperature. So if vapor is not there, vapor state is not there, then we need not consider pressure. So we need to follow F is equal to C minus P plus 1 condensed phase rule for those systems. First let us take air. Air is a mixture of various gases. We need not bother about what are the gases present in it and count it. Just take it as C is equal to 1. Number of component is equal to 1 and then P is equal to 1 because all are miscible, homogeneous phase, single phase. So P is equal to 1. So we can take this phase rule, that is F is equal to C minus P plus 2 itself. So number of component is 1, number of phase is 1. So F is equal to 2. Degrees of freedom calculated for it is 2. And whatever the gases, whether it is a single gas or many gases or only 2 gases, whatever may be, for that also the F is equal to 2. Number of component is 1 and then the number of phase is equal to 1. If you take water system, so normally when ice, which is a solid state, is in equilibrium with water and that is in equilibrium with the water vapor. Okay, so that system we call it as a water system. So in this 3 phases are there and one component, because always water is expressed as H2O, either it is in the ice form or in the water vapor form, whatever may be. So number of component is 1, phase is 3. So degrees of freedom is equal to 0. If you take any system like either ice or water vapor separately, then the number of phase is 1 here. Component is always 1, right, for water or ice, whatever may be. So 1 minus 1 plus 2 is equal to 2. If any 2 state is in equilibrium, okay, that is for example ice is in equilibrium with that of the water, or water is in equilibrium with that of water vapor, or ice is in equilibrium with that of the water vapor, like that, whatever may be, then F is equal to C, that is 1 minus P is 2 phase, 2 plus 2. So F is equal to 1 in that case. Now let us see decomposition of calcium carbonate. So for decomposition of calcium carbonate as well as for the decomposition of copper sulfate pentahydrate, the F is calculated to be 1. Let's see how. Okay, so there are so let us see the decomposition of calcium carbonate first. Calcium carbonate upon decomposition produces calcium oxide and carbon dioxide. What is the state of calcium carbonate? Solid. Calcium oxide solid. Carbon dioxide gas. So how many phases are there? 2 solid phases, 1 gas phases. So P is equal to 3. Component we did not tell here 3. Okay, we have to tell it as a 2. This is because the composition of the 2 of the component is known, then composition of the third one is automatically fixed. So in this case, which is simple, like it is like a X, that is see, calcium oxide plus carbon dioxide, if you add you get CaCO2. Like that, copper sulfate water, if you add you get this copper sulfate pentahydrate. In such cases you have to take the component to be 2, not 3. So we should be careful in that. So if you take component to be 2 and then phase to be 3, then you get degrees of freedom is equal to 1. Next, ammonium chloride. This is a very interesting one. Ammonium chloride is a solid. It produces 2 gases, ammonia and hydrogen chloride. So you should be careful that when you decompose this, you are getting HCl gases form only. Okay, so number of component here is 1. Okay, although ammonium chloride is there, ammonia is there and HCl is there, the number of components is taken to be 1. This is because ammonia and HCl in gaseous form. So if what is the composition? NH4Cl. Okay, so the composition is expressed as NH4Cl in the left hand side as well as in the right hand side. So you have to take the number of component to be equal to 1. And phases. this is one solid phase, this is a gaseous phase. You should not tell two gas phase. Gases are actually miscible. So one solid and one gas. So two phases are there. So component is 1. So degrees of freedom F is equal to 1 for the ammonium chloride decomposition. Next, let us see for salt water, saturated water and supersaturated salt water. So what is the difference? Salt water, if you put water in the, salt in the water, completely miscible. Okay, but to a certain limit only. If you go on add salt, at certain stage it gets saturated. So it gets saturated, and after that if you add one more or a little more amount, it is called as supersaturated. Supersaturated has got more salt than the saturated salt water. So this is the difference. Now let us calculate. When the water is, when the salt is completely soluble, the system has got salt as well as the water, but number of phases is 1. So I put 2 here, number of phases to be 1, so I get F is equal to 2. For saturated water, we have to take the component to be equal to 1. Okay, so take the component to be equal to 1. Phase is again 1. Okay, so you get F is equal to 1. So for salt water 2. For saturated water 1. Supersaturated water. For supersaturated water, and F is equal to the number of phase is 1. Number of component is 1 here. Saturated water means you have to put number of component to be 1. And for supersaturated, there is some salt settling, right? So 2 phases. So 2 phases, P is equal to 2. So place 1 equal to 0. So you must see here, I have used the condensed phase rule, not C minus P plus 2 here. Everywhere I used the condensed phase rule because we are not considering the vapor phase here. Pressure term should be eliminated. So for calculating the degrees of freedom for salt water or saturated water or supersaturated water, use the condensed phase rule.